Okay, thank you, Steve. So last year I was for the first time at GeoWeb 2008. It's a conference where all the vendors that do geospatial products come together, and there was last year just one talk about RDF. This year in this conference there were about 5 talks that mentioned the semantic web and RDF, and there were no recordings made of the talks, so we decided to record the talk in this particular webinar. So as Steve mentioned, the talk will be a combination of my talk. I gave a talk about geospatial capabilities and moving objects with RDF and AllegroGraph, very much aimed at people in the geospatial community, not so much at people in the RDF community. And then my colleague Steve Hafley gave a talk, very, very technical, about 2D and 3D indexing, and I'll first give you more the general overview in my talk, and then at the second half of my talk I will go really in depth about what Steve talked about indexing techniques in AllegroGraph. So for the people at the GeoWeb conference, when I was there in 2008, not many people talked about metadata. This year, nearly every talk mentioned at some point in time metadata and the need to have more ontologies. And so I came up with this slide about a Gartner slide for a list of the top 10 disruptive technologies, and one of them is semantics. And not many people at the geospatial conference had heard about semantics, so I explained to them that if you want to know more about it, go to the W3 website, and you will find some definitions of what the semantic web is all about. And actually what I really like is this recent kind of a summary of what the semantic web is about. Basically the semantic web is about 2 things. It's about common formats for integration and combination of data drawn from diverse sources, where on the original web mainly concentrated on the interchange of documents. It's also about language for recording how the data relates to real-world objects, and that allows a person or a machine to start off in one database and then move through an unending set of databases which are connected not by wires but by being about the same thing. And if you read this definition, then here you basically see a visualization of the definition. I think most people in the audience will recognize it because most of the people in the audience come from our semantic web news list. And so here you see the linked data picture where you see all the databases that are connected. And what you see here, there's a lot of connected data sources about biology, and then there's a whole bunch about publishing, scientific publishing, and other types of publishing. Then here are some social network sites, and then here is the DBpedia, the RDF version of the Wikipedia, which is the most heavily connected database in this entire set. But the second most connected one, or maybe the third, is the GeoNames database. It's a database with roughly 7 million places on Earth. And what you see, for example, is that FOAF, which is a standard for how you describe a person on the web in RDF and the friends of that person, and the places where someone lives links to the GeoNames database. The DBpedia, as the RDF version of the Wikipedia, talks about hundreds of thousands of times about places where something happens or where something is. And of course there's now links to the GeoNames. OpenCollet is an entity extractor where you take any type of text and you put it through OpenCollet, and then you get all the entities in it, and part of it is the places, and again they are linked to GeoNames, etc., etc. So a lot about things in the semantic web are already connected or have a geo encoding. And by the way, I'm going to talk a little bit more about GeoNames later, so just let me also give you straight away a little demo of GeoNames. Let's see. So here I show you a web interface to our a database called AllegroGraph, and this is a web interface to it. And here you see I have a bunch of triple stores open on one server. There's the bio-ontology with 300, 400 million triples, GeoNames 130 million triples, and Loopt 8000, a university test set with 1.1 billion triples. So it's a big server here. But let me click on GeoNames, and what you see here is some statistics about this one particular database, 131 million triples. It isn't reasoning, it's just a fairly dumb database. I do have a set of predefined queries actually. There's no free text indices, and we use all the indices that we have. But anyway, let's just look at some data in there. So let me look at the queries and say I find all the Berkeleys in the world. Yeah, so I click on this query, and here you see find every X and its coordinates, where X has the ASCII name Berkeley, and this X is at this particular coordinate, and I executed it. Well, and say let me look at the Berkeley that I live close to, and here are the RDF predicates for Berkeley. So we see that Berkeley has many alternative names in this database. PPL means that's a populated place. It's in this time zone. About 100,000 people live in Berkeley. And this is the location. Actually, we store location at 2 resolutions, and I'll talk later when I talk about why we do that, etc., etc. And so when I do this query in Sparkle, I get back a list of well, X and coordinates, and I can also, if I want to, directly display them in Google. So here you see that even in Australia there's a Berkeley, in Berkeley of course, and then a whole bunch on the East Coast. Again, let's go back and let's look at some other queries. Just to give you an idea what you can do with the GeoNames database. So let's find the Berkeley in California. And by the way, this is in Prolog. I use both Prolog and Sparkle when I deal with triple stores. I prefer slightly Prolog, so I'll give most of my queries in Prolog. But if you can read Sparkle, you can read this too. So this is the Berkeley in California, and of course now I get only one here. And then something more exciting what you can do with a database is, for example, find everything within 5 miles of the place where I live. I live in a town called Moraga. So let me do this. And what you find is, so what you say is, when you want to find everything within 5 miles of Moraga, is give me an X with the name Moraga, and then find every Y that is within 5 miles of Moraga, and then for this particular Y, find its name, and for this particular Y, find its coordinates. And I get a whole bunch of stuff. I get churches, I get post offices, I get churches, I get the city hall, etc., etc. And of course I can display that again in a map. And so you see a lot of stuff on the border with Oakland, but then here's the stuff around my town. Again, I go back and now say I only want to see the schools around within 5 miles around my town. So I click on this one, and here I get a whole bunch of schools that are within 5 miles of where I live. And if I want to see all the parks, then I can use the encoding for parks, which is, I think, PRK, and then I execute, and now I see all the parks that are within 5 miles of where I live. Okay, so this is AllegroGraph Web View, one way to play with the GeoNames database. But I'm slightly ahead of myself, so let's go back to the presentation. Where is my, oh, here it is, yeah. So again, in this talk, I will talk about why RDF needs geospatial, and it's hopefully already pretty clear by now, and why the geospatial community needs RDF. I talk about the basics of an RDF triple store, but given that most of you guys come from the semantic web list, I won't make that too long. I talk about events and about how in one query language we combine all these the geospatial, temporal, and the SNA capabilities. I already gave you one example. So I already did the GeoNames database. I will talk about a river network in GeoBC. And then we get to the second part of the talk, which is more technical. I will talk about moving objects. And then I will go into 2D indexing, which we already have in AllegroGraph, and 3D indexing, which will appear in 4.0. So why does the RDF community need geotemporal reasoning capabilities? Well, I give you the linked data, and I show that many data sources already are geospatially encoded, or they point to a resource in the GeoNames database. So I guess I don't have to say too much about that. One thing I do want to say is that with the geospatial capabilities in AllegroGraph, we in no way try to even compete with Oracle Spatial. What we are interested in, or what we try to target, is you are a person that does work with RDF, and you do geocode your data, and now you have basically very simple needs, or you want to find the distance between two places, or you want to find everything of a particular pattern within a number of miles of another place. Yeah, that's what most people do. For example, about 1.5 months ago, I went to the O'Reilly Where 2.0 conference. It's a very popular conference. This conference is only about location-based services on the web, and all the big players were there. But if you look at what people actually do with geospatial data, it's fairly simple. It's hardly any really complicated geospatial stuff going on. Now, the geospatial community also needs RDF, but they're not entirely there yet. But the story is, RDF is all about metadata, and metadata is usually very unstructured and sparse, and objects that you describe in geospatial databases are usually part of an object hierarchy. So if you have satellite pictures and you want to annotate the objects that you see in the picture, or you make maps and you describe objects there, it's again objects of a particular type with all kinds of annotations. The metadata nowadays doesn't really address that really well. So there's a growing need in the geospatial community to deal with or to create ontologies. And one project that is really focused on creating ontologies for everything in the geospatial domain is the National Map project. And there's a large group of people working on it, and I hope that the recent stimulus program gives this thing a boost, because it would be really interesting to take all the different geospatial databases in the US, which are always different in every region, in every county, and kind of be able, through ontologies, kind of all link them together. Okay, so that about why the geospatial people need RDF and vice versa. Now about graphs, triples, and triple stores. Again, I keep this very short. I always explain to people that if you have a relational database, you start with a schema. Well, in the triple store, you just open the database, and now with the triple store, now you can just say what you want to do. I can add triples. This is kind of very regular data. Person with the first name is and age. I could do just as well in a relational database. One difference with relational database is that one-to-many relationships are directly encoded. So let's link person 1 with person 2 and 3. And because it's RDF and it's a triple store, you can say whatever you want to say. You're not constrained by any schema. So I can say person 1 likes pizza. Can add more relationships, and it all goes into a graph. So things are connected through links, and that's why we call RDF stores also graph databases. Now, one thing that we do with our product a lot and with our customers is that we deal with events, whether it's customer care events or emails or telephone calls or bank transactions, etc., etc. all events, and events always have a type and maybe subtypes. Events always have actors, always have a start time. Sometimes they have a duration or end time, and in many cases events have a place where they happened. And so what we did in AllegroGraph is we designed a few libraries on top of our triple store where we deal with social network analysis, where we do temporal reasoning, and again this talk is about geospatial reasoning, so I'll go more into detail about that. And okay, so we can display, of course, that stuff in our triple store. And then if you want to do queries on your database, we've made it easy to do so by taking all the capabilities that I just talked about and put it in one query language. So if you take, for example, the this particular query, then you see here that in one query we deal with a social network. We take the ego group around the person Jans, and then we take the most important person in the group around Jans, and you find all the actors, all the events for this particular actor of a particular type, and then you look to see whether this event happened in a particular time period and whether this event happened in a particular bounding box in space. And so we integrated that all in one language, and when I gave you the GeoNames demo, you kind of saw this this syntax already. So now about the geospatial reasoning. So again, we're not here to replace Oracle Spatial. We try to keep it really, really simple. Basically, we want to make it easy if you work in RDF to find how far one event was from another event, and we want to find all the things that happened within a certain number of centimeters or kilometers, kilometers or miles around another thing. And we want to make this work on really, really large databases. So let's see. And to make it easy for you to deal with that, we created some functionality to put in your queries. Actually, these queries that you see here are defined by rules. Those rules are not in the product itself because they depend on the ways you index. So if you want to be able to use the things that you see here on this slide, then please send me an email and I'll send you the rules or I'll help you get there. So those are the primitives. We do have Sparkle. So this gives you all the places around London within 50 miles that have a population that is larger than 25,000. There's a Sparkle workgroup from around 4 vendors and a bunch of people interested in Sparkle and geospatial. So this will not be our final Sparkle syntax to deal with geospatial. I expect that later this year, early next year, we have a slightly easier and a more standardized way for Sparkle to deal with geospatial information in RDF triple stores or RDF in general. Again, we do our geospatial stuff fast because of the way we do our indexing. So when you saw me do the demo with the GeoNames database, you saw that things got back really quickly, and depending on the warmth of the database, it takes you just a few milliseconds to get everything around, say, the 3 miles around my offices. So it's a very practical thing to use if you build web services around this. One of the projects that we did was for an organization in British Columbia. The organization is called GeoBC, where we dealt with the river network, and I think I've talked about this before in my webinars, but just to keep this a little bit faithful to my talk in Vancouver, I'll include it again. So this is a river network, and if you know anything about graphs, you know that a river network is always a graph. You have here the links, and then you have always a left drainage area and a right drainage area, and you have your choice point, and here you get a new segment. And so what we did is we took the river network in British Columbia we put it in very simply in triples. So this is the way you can put it in triples. And then we were able to do queries that were really kind of impossible to do with any other type of database. Because we can say, okay, say I have a polluted area downstream, I can find all the places where the water might have come from, or if I have somewhere high in the network a polluted area, I can find all the places where the water ultimately will wind up and make it completely automatic and fast. So we combine their graph search and geospatial in one framework. Well, that is what I just explained. And then we can display it also in Google Earth. So for example, I can specify in AllegroGraph a bounding box. So here, I hope you guys can see it over the GoToMeeting link. But if I specify in AllegroGraph this bounding box here, then I will get all the all the little rivers and drainage areas that come through this particular area. Very, very useful. Okay, so that was the first part of my talk about our geospatial capabilities, and everything I talked about you already can do in AllegroGraph 3.2. So now go to the second part of my talk where I talk about moving objects. So at France we're right now doing two little projects where we work with people that do biodiversity projects. Sorry, that was not a really good sentence. And we have another paid project where we track ships near the coast of Africa. And so people that know a little bit about ships, you know that any big ship is required every 4 seconds to send its position to a central database. So let me see, I have this running here. And the system is called AIS. You can look up on the Wikipedia what it does or what it is. And let me run it. Maybe I have to get rid of this highlighter. Normal, okay. So I don't know if you on GoToMeeting really can see what is happening here, but for the last several months we have been harvesting all the vessel data or ship data for various places on Earth. This is for the Bay Area, where you can see how ships move all day through, well, to the Bay Area. I can go here. Actually, there's a YouTube video that we point to on our website because the animation doesn't really look good here. But this data comes directly streaming out of AllegroGraph, and it's very interesting to look at this data. But let me go back to my presentation. Yeah, so we see many opportunities for dealing with moving objects. For example, in the telecom space, most of you probably will be familiar with an iPhone application called Loopt, which is already tracking all your friends. But there's also a biology project where the data is available about, say, birds and their migration patterns, and this stuff is now also all in RDF. And the challenge that you have with moving objects in any database, including an RDF database, is you, in theory, want to track millions of objects at a resolution of once per minute, or say for every change in so many meters. And you need to do it in real time because you want to be able instantly to use rules to look at current configurations in your data and take actions, for example, in the telecom service or with ships. But you also want to store all your data, possibly not all your data because it might be too much, but most of your data, and then later on do analysis on where ships went, where birds went, etc., etc. And you want to do even predictions. Now, kinds of questions that we use as use cases for our research and our work with moving objects is, say, do we have 5 soldiers that have been active less than 8 hours? The training X and equipment Y within a mile distance of each other? Or, where you do a little bit of prediction, find another truck that can pick up package X at location Y, so I can pick up package A at location B, so that we both will arrive at P before time T. Yeah. So these are really challenging ones to do, and especially on really large data sets. Now so far what we've implemented real time is we use some kind of gaming approach to do 3D indexing in memory. So all the active objects are kept in memory, and then you have some aggregation rules where you make sure, or filtering rules, where you don't save everything for every moving object, but just the relevant stuff, so that you can later do historic analysis. And for that we had to work both on our 2D indexing techniques and our 3D indexing techniques. So now I go a little bit more into Steve Havlik's talk. Steve talked a little bit about 2D indexing, which is already in AGraph 3.2, and then he talked about 3D indexing, which will be in AG 4.0 or close thereafter. And I put this book here because this is about 1,000 pages on doing multi-dimensional indexing, and it was a big inspiration to Steve while he was doing this work. Very interesting book. So when Steve gives this talk, he usually starts with this picture. He studied at MIT 30 years ago, and he had one of these card sorting machines, and there was a big sign above one of these machines, and it said, "Happiness is sorting things in n-log time." And that was true in the day of card sorting machines, but it's still true in our days. Yeah, you have to store a lot of data on disk. You can't get much faster than n-log n in time, and in AllegroGraph we did a lot of work to make sure that we keep all the data always linear, close to each other. However, that's great if the data is linearly sortable, but what do you do when it's in 2 dimensions or 3 dimensions? But anyway, let's look at 2 dimensions first. So if you guys, for the people that have been playing with AllegroGraph or using AllegroGraph, you know that we have various indices. Basically we sort our triples in every possible way so that whatever we want to get out of the data triple store, we can kind of directly get to the right spot on disk. And that works perfectly for 2D. So if you have ages or dates or times or currency, I mean that all works fine with sorting. But what do you do when you have Cartesian or spherical coordinates? I mean, they're not orderable and sortable. So how do you integrate it in the AllegroGraph model? And so you want to find linear happiness in higher dimensions. And the most important problem is proximity search. Yeah? So you have XY data, and lots of them. And say you want to find everything within the circle on in this particular polygon, and you want to do as fast as possible. Now, the wrong way, and everyone in the database community knows that, is that you say sort both or have an index on X and Y, because the problem is there is that if you say sort on X first, then you have to do a join with the Y, or if you do look up Y first, then you have to do a join with the X. So you have to just look at too many places in your database. And in AllegroGraph we can't use R trees. That doesn't fit with our model. So we came up with another model. So we said what you really want to do is when you have a whole bunch of data points, then it would be ideal if you just could look in the area where the things are that you're interested in. But how do you do it? Well, for us the eureka moment was to think in strips. So basically what we do is we always divide the world or a small Cartesian place into strips, so vertically. And then we keep everything sorted within a strip. And so if you search for something that is the same size as the strip size, then you always have to look in 2 strips, but that's only a very, very small part of your data. And you can't even get lucky, because if the thing you're looking for, the circle, is smaller than the strip width, then you might even have to look in a small strip. But then sometimes you just get bigger, and you would have to look in many, many strips. but always we reduce the search to a small part of the database. So if I summarize what we do with 2D, is you have to tell the system what the strip size is that you want to work with. And that's kind of inconvenient. You would like to read it completely automatic, but again, it's also in relational databases where you define different types of indices on the same geospatial data. But you can make mistakes, so even if you choose the wrong strip width, you always get a result back. Even when you make a mistake in the order of magnitude. 2 orders of magnitude, it gets really slow, but if you stay within the order of magnitude, your performance will be good. Okay, so that is about 2D, and now let's go to 3D. So basically what we do for 3D is the same thing for 2D, but now it's not strips, but it's cubes, or actually prisms. Yeah, so now we have an X and a Y and a T, or TXY, or XYZ. So, but anyway, there's many ways you can use 3 dimensions, and again, we came up with a sorting mechanism and an encoding mechanism where again you have to look at only a very small part of your database. So we use strips, but now 3D strips, actually blocks, and as I said, the dimensions can be anything, X, Y, Z, let alone altitude, etc., etc. And by the way, we're even working on 4 dimensions, but let's talk about it now. And I'm not going into this particular slide because it takes too long, but if you go to our documentation on the AllegroGraph website and you look for geospatial, you will find the documentation how we do 2D indexing in far more detail, and the 3D is just a variation on that theme. And then one of the things that Steve talked about in his talk in Vancouver, and which we also describe in a paper real soon, is to look at various ways, or various types of queries that get harder and harder. The most simple query is to find just some, so you have a thing with an X, Y, and a T. Let me use that for our examples, and you just want to find something that's very close to that. Well then, in example, you have to just look for a few blocks, and that's it, depending on how big your strip size and how big your search radius was. It gets a little bit harder when you want to find 2 moving objects wherever within a given distance. Now you have to traverse already many more blocks in the database. Even harder is it when you have a given one moving object, detect all the other moving objects that were ever within a given distance, and we still can do this stuff in kind of linear time. It gets much harder if you find all occurrences of 2 moving objects. So you have a database and say, oh, give me any 2 moving objects that were within a certain distance of each other, whether it were 2 ships or 2 birds or whatever. Now, you don't know which of the moving objects is important, so you need to traverse and compare each pair of the moving objects, and basically you almost scan the entire database. We're working on an algorithm where we kind of can still do 2 linear scans through the entire database and move 2 cursors forward and do the comparisons. So we still have high hopes that we can solve this in well, n log n time. Well, it's probably going to be more than that. But what we haven't even solved yet, and we only seen as a difficulty, is how do you find objects that are as a click together? So for people that are familiar with, say, social network analysis, you know, there's a particular type of graph, which is the fully connected graph, where everyone knows each other. Yeah, I can have a home click or a family click or a school click. Everyone that click in that particular graph is connected. But you could have a connection graph for space too. So you might want to look for ships. Which ships are always close together and always move together closely? Well, that's a really, really hard problem to solve. And but again, it's a very interesting research question. So summarizing, 2D, 3D, 4D. 2D, 3D, 4D. 3D, 4D, 5D. 5D, 6D, 7D. 7D, 8D. 8D, 9D. 9D, 10D. 10D, 11D. 11D, 12D. 12D, 13D. 13D, 14D. 14D, 15D. 15D, 16D. 16D, 17D. 17D, 18D. 18D, 19D. 19D, 20D. 20D, 21D. 21D, 22D. 22D, 23D. 23D, 24D. 24D, 25D. 25D, 26D. 26D, 27D. 27D, 28D. 28D, 29D. 29D, 30D. 31D. 31D, 32D. 32D, 33D. 33D, 34D. 34D, 35D. 35D, 36D. 36D, 37D. 37D, 38D. 38D, 39D. 39D, 40D. 40D, 41D. 41D, 42D. 42D, 43D. 44D, 45D. 45D, 46D. 46D, 47D. 47D, 48D. 48D, 49D. 49D, 50 Yeah, I gave you a lot of information this day. Usually I keep my webinars a lot shorter, but to summarize, you can do 2D geospatial and temporal now in AG 3.2, and I gave you some types of queries that you can do in AllegroGraph WebView. You can expect 3D indexing in 4.0 or maybe just after that. It's very important for us that we get 4.0 out as soon as possible, and if we get 3D in, it will be in, otherwise it will be slightly after that. We are looking to help people that want to do projects with moving objects. We're already doing a few projects, but if you have a application where you need to work with moving objects, we're more than happy to help. And as I do in all my talks, we're looking for 4.0 testers. So thank you very much.